Okay, so welcome to this video, just covering chapter 1.2, which is stable and unstable nuclei. You should have already done some work now which covers the facts you need to know about the strong nuclear force and its role in keeping the atoms stable. What we're going to look at in this video is what happens when a nucleus is unstable, and for that we're going to think about what happens when it emits either an alpha, beta minus or gamma emission, and calculate mass and atomic numbers after those. Now notice there, we'll specify this is beta minus emission. We'll meet beta plus emission later on. Okay, so first of all, let's have a look at what happens in alpha emission. So alpha particles, you remember from GCSE, consist of 2 protons and 2 neutrons. So we could write it as an alpha particle, mass number 4, atomic number of 2. Now, that is identical to a helium nucleus, as some people will often write it like this, helium-4-2. However, if you do write it as that, you've got to bear in mind that it is not a helium atom because it doesn't have any electrons. It is just a helium nucleus. So, actually writing it as alpha particle is a lot less, if you like, ambiguous and a lot more obvious with what you're dealing with. So let's have a look at what happens in alpha emission. So here's a little diagram showing the parent nucleus and the alpha particle being emitted. Of course, that's not the whole story. So typical alpha emitter would be uranium-238. And uranium atomic number 92. So if it emits this alpha particle, which has a mass number of 4 and an atomic number of 2, there's got to be something left over. Okay, we call that the daughter nucleus, really. But what it is going to be something of a mass number of 234, because 238 we started with. We've kicked 4 units of mass out in terms of the alpha particle, so we're left with 234. And we also can work out that the atomic number of the thing left over must be 90. Because we started with 92, we booted 2 out of the nucleus, 2 protons out of the nucleus, so we must be left with 90 protons rather in there. Did I just say neutrons? I meant protons, sorry. And what we then need to do is think about what nucleus or what atom that would be, and looking it up on the periodic table, that would then be thorium. Okay, so if we have got alpha emission, then the mass number goes down by 4, and the atomic number goes down by 2. Next up is beta minus emission. Now, as I say, there is something called beta plus emission, which we'll learn about sort of later on in the chapter. Okay, so again, from GCSE, you should remember that beta minus particles is in fact a fast-moving electron. Okay, now there's a problem there, if you remember, because all 3 types of radiation come from the nucleus. There are no electrons in the nucleus, of course. So what is happening? Well, what you'll have learned at GCSE is that in the nucleus, 1 neutron turns into 1 proton, plus the beta minus particle or the electron, and it's that beta minus particle that then gets instantly kicked out of the nucleus. Now, at AS, we need to have a little bit more information than that, so we need to just think a little bit more about what's going on. And in fact, there is another particle that is also released at the same time, demonstrated by this little diagram down here. The neutron does indeed turn into a proton and electron, but we also have this other particle released here, which again we'll learn about slightly more as we go through the particle stuff. But this particle here is a tiny, almost undetectable particle, and this is an electron type antineutrino. Okay. This bar, well, this sort of slanty V symbol is the symbol for a neutrino. The bar above it indicates it's an antiparticle, and the small subscript E tells us it's an electron-type antineutrino. There are, in fact, 2 more different types of neutrinos and antineutrinos, though you only need 1 more type for your syllabus, but again, we'll come back to that later. Okay, so let's have a look at this diagram then. Suppose here what we've got is an atom of carbon-14, And fairly obviously, looking at that diagram, that is not an accurate graphical representation of carbon-14. That decays by beta minus emission. So remember what happens, one neutron turns into a proton plus the beta particle plus this antineutrino. So if you think about the mass number, first of all, of the nucleus that's going to be left over, it's lost a neutron, but it's gained a proton. The mass number is the number of protons plus neutrons, so that is actually going to stay the same. Okay, so in beta minus emission, the mass number stays the same. What's going to happen to the atomic number? Right, well, we start with 6 protons, but now a neutron has turned into a proton, so we've gained an extra proton. So we've now got 7 of those. Again, we would look that up on a periodic table. Anything with 7 protons is nitrogen. We then have to put in these other particles. So we've got the beta minus particle and the electron antineutrino. The electron antineutrino has a mass number of 0, atomic number of 0. The beta minus particle, which is an electron, so it's got no protons or neutrons, so it's got a mass number of 0. Now, its atomic number we always write as -1. Obviously, it isn't -1 protons, but we had 6 on the bottom line to start with. After it must balance, so 7 minus 1 plus 0 is still 6. So that's why we write the proton or atomic number of the beta minus as -1, so that we can balance the atomic numbers before and after the arrow. And it also gives us a useful reminder of the charge of the beta minus particle. If it's an electron, it has to have a charge of -1. So again, all that should be revision from GCSE, except for, every time I make one of these videos the bell goes, so all that should be revision from GCSE, except for the inclusion of the electron antineutrino, which is new. And as I say, we'll go through that in more detail later, so for now, just remember that you have to include that particle as well when you're showing beta minus emission. Finally, let's look at gamma emission. Gamma emission is the easiest one of them all, because the gamma emission, or the gamma radiation, is, as you'll remember from GCSE, an electromagnetic wave. Okay? So an electromagnetic wave is simply energy. So when a unstable nucleus has emitted either an alpha or a beta particle, chances are the nucleus will be in what we call an excited state. In other words, it's got too much energy. Okay, so it needs to get rid of some energy. So to do that, it emits this gamma wave, which is just an electromagnetic wave. So the nucleus, in terms of the number of protons and neutrons, does not change. It goes from one with lots of energy to one with a bit less energy to make it stable. So if you have a look at this diagram here, you can see here that when we start off with this unstable isotope, it's got a mass number of 137 and an atomic number of 56. It emits the gamma wave, and it's still got a mass number of 137 and an atomic number of 56. Now look at this word here. I've described the gamma wave as an electromagnetic wave, which is what you'll be familiar with. Here, it is being described as a gamma photon. Now, the existence of photons, that is a new model of light. Previously, we've thought of light as a wave. As we will see in Chapter 3, just thinking of light as a wave does not explain certain physical phenomena. And, in fact, this model of light as a stream of photons, which are sort of tiny particles, if you like, we'll meet in Chapter 3. It's what Einstein got his Nobel Prize for. So for now, just bear in mind that gamma waves do not change the actual physical structure of a nucleus. They just get rid of some energy. And just be aware that as well as calling gamma waves electromagnetic waves, we can also describe them as being a stream of photons as well. Two models to describe the same thing. Okay, so you should be able to solve these yourself. 3 nuclear decay equations: plutonium, which decays by alpha; strontium, which decays by beta minus; and technetium, which decays by gamma emission. Let's give you a few seconds just to fill in what the missing remaining nucleus and any of the particles are on those nuclear decay equations. Okay, so let's have a look at these. Well, we know that the mass number of alpha is 4, atomic number 2. That is going to leave us with 240 as the mass number, 92 as the atomic number, and when you look at that, 92 protons is uranium. With the beta particles, remember that we said they had a mass of 0 and an atomic number of -1. Or you can think about one neutron turning into a proton plus an electron. So the mass number is going to stay the same. The atomic number is going to go up by 1 because we gain a proton. And again, when you look that up, that is then yttrium. New thing now, in addition to your GCSE knowledge, that also emits an electron antineutrino. Don't forget that, it's important. The gamma 1, dead easy, no changes at all in the actual physical structure of the nucleus. So technetium-98 emits a gamma wave, or gamma photon, and it is still technetium-98.